Okay. It's a beautiful spring day, so why not have an organic chemistry class? Yeah, I'm getting a little spring fever too, but we're only about halfway through the semester, so hang in there. This early spring, I don't know. Okay, let's just remind you what we talked about on Monday, and then continue from here. So we're talking about stereochemistry of molecules now in a different way, and that is in the idea that molecules, particularly with carbons that are asymmetric, that is carbon with 4 different groups attached in a tetrahedral structure, has a different stereoisomer available, which is a mirror image of the molecule. So if a molecule lacks any kind of symmetry, in particular if you have a molecule which has a plane asymmetry, like shown in the bottom here, you take a mirror image of that and it's going to be identical. But if a molecule has all 4 different groups, the mirror image is no longer identical, even though all the atoms are bonded the same. So what do we call the relationship between these two molecules then? Do you remember the term?
Enantiomers?
Yes, enantiomers. These are enantiomers. And they are chiral. Enantiomers. Sorry, my writing's terrible. Enantiomers. Chirality is the ability to have different mirror images, and specifically this type of stereoisomers, which are mirror images of each other. They're related as a pair of enantiomers. So remember these terms we talked about, molecules that are not superimposable on their mirror image. And when we use this term enantiomer, we're talking about a relationship between 2 isomers. Okay? And so we're going to be learning a number of terms like this to describe different kinds of isomers. We talked about constitutional isomers and stereoisomers in a bigger picture, but there are now, we're learning different kinds of stereoisomers. These are chiral molecules. Molecules which are not chiral are often referred to as achiral. Achiral. And lots of different terms to refer to the center of chirality in a molecule, or a carbon which is asymmetric, or a stereogenic carbon. People use all kinds of different terms. A chiral center, a chiral carbon, center of chirality, stereogenic, I prefer stereogenic carbon, or center, or stereogenic center, when we were talking about a specific asymmetric carbon within a molecule. So that's some terms, and we'll be learning more terms as we go along. Remember that molecules that are different only by the fact that they are mirror images of each other, that are enantiomers, only show differences in their physical property of how they interact with plane polarized light, something we refer to as optical activity. So remember, if you have light which is polarized in one direction, in one plane, and you pass that through a sample of a molecule which is chiral, whose mirror image would be something different, the orientation of that light changes as it interacts with those chiral molecules. And if you have one mirror image or the other, it'll bend it the same amount out of plane in opposite directions. And we have a specific optical activity, or a specific rotation we talk about, which refers to that with this formula. You don't have to remember this formula, but I want you to understand if you do see these kinds of numbers reported in your future, that you know that that's accounted for by the rotation of that light divided by the sample size, basically, the length and the concentration. So each molecule that light interacts with twists that light a little bit more. So it has to be normalized for the specific sample size that you have. So you can compare one number to another depending on who took the measurement. Another term for you, racemic mixture, or a mixture of racemates. A racemic mixture is a mixture of enantiomers that happens to be exactly 50-50. So that would actually show no optical activity if you tried to measure the plane polarized light passing through a racemic mixture, because as I said, the two different mirror image molecules bend like equally in opposite directions. And so if you have a 50-50 mixture, they'll cancel out. Okay? So we would say it's not that solution is not optically active. Doesn't mean what's in it isn't chiral, but it could be a 50-50 mixture or a racemic mixture of enantiomers. Okay? And finally, we ended on Monday talking about how we name the molecules that are different stereoisomers based on their mirror images. And we refer to that with an S or an R designation to indicate a specific carbon that's asymmetric or a stereogenic carbon in that molecule. These molecules that I'm showing here, 2-chlorobutane, happen to have one stereogenic carbon in it. There are molecules with more than one stereogenic carbon, and so you have to account for all of them. And they could each have different configurations at that specific carbon. So we use R for right or clockwise, going from the highest priority group to the lowest priority group of the top three. And we use S or sinister, the Latin term for left, to indicate it counterclockwise. And remember, it's important to visualize this properly and orient the molecule properly when you try to make these designations. So remember the Kahn-Ingold-Prelog rules for figuring out the priorities. So in this case, atomic number chlorine, carbon, carbon, hydrogen, we can easily see which is the highest priority and which is the lowest priority, right? Chlorine is the highest, hence I put a number 1, and the hydrogen is the lowest, 4. And you look at the molecule by pointing the lowest priority group away from you. So in this case, the hydrogen is already going away. And then we arrange the priorities of the next three groups. So using the same systematic rules we use for determining priorities for E and Z in double bonds, we can identify that this ethyl group here has a priority 2, and the methyl is third in terms of priority. So hydrogen pointing away, you rotate clockwise, going from 1 to 2 to 3, and you can see that that would have the S configuration for that stereoisomer. Okay. Anybody have questions about that? We're going to show some more examples in a minute. Remember, there's that nice, easy trick to look at these molecules by using your hand. So if you point your thumb in the direction of the lowest priority group, in this case they use A, B, C, D, highest to lowest, you can have that molecule oriented however you want on the page and try to just align your hand with that, and it makes it a little bit easier. So if your hand curls in the direction of highest to lowest priority, if your thumb is pointing where the lowest group is, depending on which hand you need to use, you have left hand for S and right hand for R. So this one, for example, hydrogen pointing back, and your thumb needs to point to the back and your hand curls to the right. You need your right hand to do it. Okay. Make sure you put your thumb in the right way. Don't do it that way. That's wrong. Left hand would be wrong because it's going to the back. Okay, so I know on the next exam, I'm going to see everybody doing their exam, and you're all going like this. This happens every year. It works. It really does work. Okay, so let's take a look at this. We saw this molecule, so let's go through this one more time, this particular example. And remember, we can draw molecules in all different orientations on the page. And we leave the hydrogens off most of the time when we draw these line structures. So it really is important to know what's attached to the carbons and what direction they are. So to remind you, when we draw molecules, we tend to draw these line structures in a way which tries to reflect the geometry of carbon being tetrahedral. And so you have this sort of this chain in the open configuration of the chain. Whenever you have a chain like that, right, if I have two groups in the plane of the board, okay, one group has to be coming out towards us, and another group has to be going away. Notice the way I drew that. Okay? I drew that where if this angle is pointing up, the other two groups coming out and back are also pointing up away from that. That looks like a proper tetrahedral. A bad way to draw that, and trust me, I've seen it, is to draw it like this, where someone might do that. Okay, that doesn't look very good drawn in 2 dimensions to point this down, because it doesn't look like a tetrahedral to us when we're thinking about space. Okay, so I would say try not to do that. That shouldn't be drawn there. That should be drawn back here, pointing up, because of the tetrahedral nature of the carbon. Okay. So it does make a difference how you draw things and where you orient them. So as you draw molecules in practice, please be careful about that. So in this molecule, well, you'll notice I drew this with the 2 bonds that are in the plane of the board going like that. But I could draw that in a different way. I could draw it like this. Okay, the 2 bonds that are in the plane of the board, here's the carbon, right? So then where would I draw the group coming up and the group going away to represent that tetrahedral carbon? Well, if I drew before like this, the up and away was pointed in the direction of that angle. So here the angle is pointing in this direction. So I would put, say, up here and away like that. Okay. I could put up here. You know, you can draw all kinds of, well, that's the same as I had before. Anyway, get used to being able to see how we're drawing things and how that translates to a 3-dimensional structure. It's important to be able to see that. Okay? Okay, after that, let's go on and look at this example then. This molecule has 2 asymmetric centers in it. So I'll just start with this one with the oxygen. So here's an asymmetric carbon. The two bonds in the longer chain are in the plane of the board. This oxygen bond is bold, so that's coming up towards us. And the hydrogen now, I'll draw it in here for clarity, is going back away from the board. So that's one of the easiest scenarios to draw this like this to show the stereochemistry or figure out the configuration, right? So all we need to do now is assign the priorities of the groups. Hydrogen, if there's a hydrogen on the carbon, that's going to always be lowest priority. Okay, there are stereogenic carbons that have 4 groups which are not hydrogen, so be careful of that. Most of the time there is a hydrogen, however, so that's number 4. The oxygen is going to be number 1. Okay, and now we have 2 carbons. We have a carbon here and a carbon here, which is number 2 priority, and which is number 3. Yeah, you go out one at a time. So the carbon on the left is attached to a C, an H, and an N. And it's that N which is going to take precedence, because this is attached to a C, and an H. So you go as far as you need to make the distinction based on atomic number. So this is going to be 2nd priority, and that's going to be 3rd priority for that asymmetric carbon. Okay? And I point that out because you don't even consider any of that when you then start to look at that asymmetric carbon. So what's the configuration here? R, that's right. You go from 1 to 2 to 3. The lowest group is pointing back already. So it's going in a clockwise direction, and you need to use your right hand to do that. Okay? Okay, so that configuration is R. All right, now let's take a look at the other one. Here, we have a carbon. Now we're looking at a different carbon, so the 4 groups we're looking at are the ones attached to this one. The hydrogen coming up towards us is going to be the 4th priority. The nitrogen going back is would be number 1. And now we have this carbon and that carbon to distinguish. Okay, so which is 2? Yeah, the one on the right is 2 because this carbon is attached to an oxygen, a hydrogen, and another carbon. This one is attached to an oxygen and 2 hydrogens. So this would be number 2 priority, and that would be number 3 priority for that asymmetric carbon. All right? So assigning the configuration here, going from 1 to 2 to 3, we're going clockwise to the right, but our lowest group isn't pointed away from us. It's pointed towards us. So you take the opposite of that. Or imagine, you know, if you can imagine looking from behind, you're going counterclockwise around there, from looking from behind it. Or you need your left hand to do that, right? Pointing your thumb out where the hydrogen is pointed out. So that would be the S configuration. So all in all, then this is the S configuration and this is the R configuration. And I'm not going to name that whole complicated molecule, but in the name, when we refer to the numbers, like 2, we would put 2S. So that's number 2 carbon, 2 carbon, 3 carbon. 2S, 3R would be at the beginning of the name to indicate the stereochemistry for those stereogenic carbons that are there. And then you would go on with the rest of it. Okay. So if you only have one stereogenic carbon, you don't have to give a number because it's the only carbon with a possibility of having 2 different configurations, right? If you have more than one stereogenic carbon, like in this example, then you have to associate the configuration with the carbon number at the beginning of the name.
And then we're also going to be including in this too the E and Z.
And then, right, so that's why this name would be really complicated. I'm not going to worry about it. I wouldn't have you actually name something like that with a full name. But yeah, you're going to have an E double bond or a trans double bond in there, and then you have different functional groups that you have to name, different side chains and things like that. So, yes. But for the stereochemistry, that's how we indicate the configuration. Okay, here are a couple of amino acids. Amino acid alanine and amino acid proline. They're amino acids because they have an amine functional group and a carboxylic acid functional group. These are the building blocks of proteins, and they are chiral. They have one stereogenic center each, so let's take a look at this. Hopefully it should be pretty easy to see, right? Hydrogen here. Hydrogen is the lowest priority group. Okay, we have nitrogen, carbon, and carbon. Okay, this should be getting easy now, right? Nitrogen is going to be the highest priority, highest atomic number. Second in priority would be the carbon attached to the oxygens, and the third in priority is going to be the methyl group, the CH3. So 1 to 2 to 3 goes clockwise with the hydrogen coming towards us, and you need your left hand to do that. So that's an S configuration. Okay. And the one on the right, very similar. It's actually almost identical. We have a carbon, hydrogen is lowest, nitrogen is highest. This carbon with the oxygens is going to be 2, and the carbon that's just a CH2 group will be 3. Okay, so this configuration is S, exactly. See? It's getting easier, right? The more you see. Let me draw another example here. Let's see. Okay, how about this one? That's also the amino acid alanine. Is it the same configuration as I drew here, or different? If you remember, this one was the S configuration. Okay. That's the same molecule, I just drew it in a different way on the page. But is it the enantiomer, or is it the same configuration? This one's a little bit more difficult because it's a little bit harder to see. The hydrogen is written in the plane of the board. Okay? And there may be examples like this that you'll see. It's easiest if the hydrogen is not in the plane of the board, because you know it's coming up or going back. But if it's in the plane of the board, it's harder to visualize. So our priorities, 1 here, 2 for the CO2H, 3 for the methyl, and 4 for the hydrogen. And if you're going to look at this with the hydrogen pointing away from us, you've got to envision your eye looking down this direction, right? So that would look something like, if we think about a Newman projection with the hydrogen going back away from us, we would have NH2 here, CO2H, and CH3 like that. Okay, with the hydrogen going straight back. So there it should be pretty easy. You go counterclockwise, it has to be S, right? So it is the same configuration. But visualizing that and looking at it from the right angle is a little difficult. It's much easier if you point your thumb in the direction of the hydrogen. And then you can go nitrogen towards us to the number 2 in the back using your left hand. If you try to use your right hand, okay, let's see, right hand pointing this way, then you're curling the wrong way. So you need your left hand. Got it? Okay, so be careful when your lowest priority group is in the plane. It can sometimes be a little misleading how you're looking at it. And again, the more you see and visualize in 3 dimensions, the easier it becomes. Let's see. Okay, here's a molecule, glucose. Let's see if you can do some of these. Glucose has 1, 2, 3, 4, 5 carbons, which are stereogenic centers. So each one of these has a specific R or S configuration. Okay, so let's just take a look at this one. Where'd it go? There it is. Let's take a look at that one. That carbon right there. Hydrogen going to the back. Okay. We have oxygen, carbon, and carbon. First priority will be oxygen, right? Second priority. We're looking at this for this. Yeah, the second priority is going to be this carbon on the left because that's a C bonded to an O, H, C, and up there is a C bonded to an O, H, H. Okay, so remember, and again, if you're having trouble seeing that, go ahead and write it out. This carbon on the top is a C bonded to an O, H, H, and this carbon here is a C bonded to an O, H, C. And there you can see there's a difference. Okay. If you have trouble seeing it, write it all out. So 1, 2, 3, that has the configuration R. Okay. Some of these get a little bit more difficult, like some of these carbons here. Which has higher priority, this one or this one? If you're looking at that carbon. Okay, this one or this one? That's a good question. Let me wipe this clean. Okay, again, we're looking at this. We know this is 1. And so we're looking at that carbon versus that carbon. You can't tell just by simple inspection, right, that easily. You have to be really careful. So if we look at this one on the top, from this bond to here, it's a C bonded to an O, C, H, okay? And this carbon on the bottom is a C bonded to an O, C, H. You can't make a difference right there, can you? You need to go farther. So you need to look at the next carbon away here. Okay, the top one, in the top case, this is a C bonded to a CHO. And in the bottom one, it's a C bonded to an OOH. Okay, so that has two oxygens. This has one oxygen. Guess which gets priority? This direction down to the right. So that's second priority, that's third priority. We had to go out a little bit further to see that. Okay. So that would have the, now hydrogen's going to the back, that had the S configuration. Okay. Let's see. Let's just take something like this. Okay? This molecule is chiral. That's a much more complicated molecule. How many stereocenters are in this molecule? 6 stereocenters? How many carbons have 4 different groups attached? There are only 3. Okay. This carbon, I'll highlight them in red. That carbon, and that carbon are all tetrahedral. By the way, in order to be a stereogenic carbon, it has to be sp3 tetrahedral with 4 different groups attached. So those 3 carbons have 4 different groups attached. The other 3 carbons in that ring are CH2s, and the ones in that benzene ring are all sp2 hydrogens. So this is a little bit more difficult. You have to understand the 3-dimensional description that I'm drawing this molecule in. Okay, this happens to have a hydrogen which is coming up towards us here, and there's a hydrogen going back here, and in this case there's a hydrogen pointed down. So would you be able to visualize that and determine the R&S configurations? Using your hand is probably the best way. And then getting your priority. So I'll just let you know, this one has what, priority 1, 2, 3. That's going to be an S configuration. This one back here is 1, 2, 3. That's going to be an R configuration. And this is going to be 1, 2, 3. That's also going to be R. Okay. Hard to do. I know it's going to be hard for you to do it that quickly, but if you have difficulty seeing that, make a model and practice that one and really take a look at it.
Is that one, when you've got the nitrogen, is that attached to cyclohexane ring?
Oops, sorry, I just erased the whole thing.
Was that a cyclohexane?
The one hanging off?
No, the one that had the one was not benzene, but yeah, that one. Is that a?
This is a cyclohexane, right? It just happens to have a nitrogen bridging one end of the cyclohexane to the other. Yeah, exactly right. Okay. Those are all the configurations. They're listed in your notes for each one of those, and you might want to go through the ones that we didn't go through and confirm that you see the same configuration. If I have a mistake on there, let me know. I think they're right though. But practice this because it does help you continue to visualize and understand the 3-dimensionality of these molecules. There's another way in which we can have mirror image isomers. It's less common, but it is present, and that is molecules which actually don't have a center of chirality. They don't have a carbon which is asymmetric or has 4 different groups attached, but because of the molecule being restricted in rotation and fixed, it could have mirror images. And this is what we refer to as atrope isomers as a type of how we can get enantiomers. I don't know if your book has that word in it. Atrope isomer. That is, molecules which are different because the rotation is restricted about a single bond. Okay, we've talked about double bonds having restricted rotation, but because groups take up space, there are cases where rotation is difficult. So if you take a look at these rings, these are all 6-membered rings that have all sp2 hybridized carbons. They're flat. Okay, but if you think about the three-dimensional nature of that, you can see that you can have those rings twisted around that single bond, okay, where the two flat rings could be in the same plane or tilted out of the plane. And as a matter of fact, this molecule on the left, which we call biphenyl, this molecule can rotate freely at room temperature. There's nothing that stops it. Okay, I happen to draw one particular conformation showing those two rings perpendicular to each other. Okay, but in fact, this is rotating rapidly. Okay, if you have a situation now where you have groups attached, so in this case, that single bond between those two rings can't rotate freely. Okay, this ethyl group and that chlorine group, they are large and take up space. And we have a bromine here and a CH3 here, and so if you tried to rotate it, it couldn't go very far because they just bump into each other. All right? So there is a possibility that that molecule can't rotate around to the other way, to the way I've drawn on the right. Those are different isomers. And as a matter of fact, they're mirror images of each other. So they are enantiomers, even though there are no asymmetric carbons in the molecule. So it is possible to have chirality in molecules which don't necessarily have an asymmetric carbon. These are just some examples. These ones on the bottom are commonly used for organic synthesis and catalysis. And so what we have is a similar situation. Here's a single bond between these two large rings, and what happens is, and I'll just draw this exaggerating the length of the bond a little bit here. So if you think about the hydrogen, which isn't drawn here, okay, right? You can see that those are such that those rings would bump into each other if it tried to rotate too far. And so they are also perpendicular, and they can't rotate around all the way around the other side. Okay, that's also an example of molecules which are restricted rotation. So in this case on the left, this ring is coming out towards us and the OH is going to the back. In the molecule on the right, that's flipped around the other way. Those are mirror image isomers of each other. Harder to see in this flat orientation, but if you can get a model, I'll just draw exaggerating these lengths again to show you. That's in the back. That those can't interconvert, at least not without a lot of energy. So these do show up. So if anyone ever asks you, is it possible to have enantiomers without stereogenic carbons or asymmetric carbons, the answer is yes. Something we refer to as axial chirality. Axial chirality, as opposed to a configurational difference in a stereogenic carbon. Okay? I want you to be aware of this because they exist. I'm not going to worry too much about knowing the specifics of how we name these R&S. There's a slightly different method, a little more complicated for figuring out which one is one configuration or the other. It's really the stereogenic carbons examples that is most important for that. Okay, so axial chirality exists. The consequence of reactions also is that reactions that we do, reactions we've talked about, can produce molecules which are chiral. So if you take a look at the reaction of electrophilic addition of HBr to a double bond that we talked a lot about, this reaction produces 2-bromobutane, sorry, this is pentane, right? 2-bromopentane as the product. But now we know that this product, the way we have this drawn, we have carbons, which are asymmetric. So let me draw the hydrogen here. That produces carbons with 4 different groups attached. So it can exist in either mirror image configuration. Okay, the hydrogen and the bromine could be up or down, depending. Okay. In this reaction, we start with some molecule which is achiral. Okay, there is no chirality in our starting material. Okay, so the only thing we can produce in a reaction like this is to get a 50-50 mixture. The only way you can do a reaction which generates a new stereocenter, the only way you can control the configuration of that stereocenter is to have something else chiral impacting that reaction. Okay? And if we look at the mechanism that we're well familiar with now for this process, we do electrophilic addition of the proton, hydrogen, to the double bond, right? That produces a carbocation on the secondary or more substituted carbon. We know that's an sp2 hybridized carbon. It's planar, right? Those two, those two bonds, if we think about it going to the back and the hydrogen is coming towards us. The p orbital exists above and below that plane. So that bromide, when it adds, could form a bond equally likely from the top, in which case, if it adds to the top, we'll get this product on the left, R. And if the bromine adds to the bottom, we'll get this product, S, on the right. Okay? Without anything else chiral in this reaction, you have to get a 50-50 mixture. There's no way to distinguish one side over the other. Okay? So reactions without anything chiral involved in it have to produce racemic mixtures if they form a new stereocenter. This is one of the big challenges in organic synthesis. How do we control which enantiomer, which mirror image of the molecule that we produce? We can do that by having chirality on our molecule. Here, for example, let me just erase this stuff. What if I had, let's say, I had another stereocenter next to this? Let's say I had a CH3 group here. Okay? And I had this molecule as enantiomerically pure, one enantiomer, one mirror image. If I have one mirror image, then it's chiral. It's a chiral starting material, not an achiral starting material. Okay, this happens to be the R configuration. All right. Now I carry out this reaction. How does that change the overall process? Well, let's take a look at it. If that carbocation, and I'm trying to look at it from the side, that carbocation, let's say, has a CH3 group up and a hydrogen down. Those are both going to the back. And these are coming towards us here. Okay? See that tetrahedron there? I'm trying to look at this from the side. So now we have a difference. For this p orbital next to that, there's a difference in the steric environment, or the crowdedness, on the top versus the bottom. Okay? Here, it's more crowded at the top. Here, there's more open space. Okay? So what would you predict then? Let me just draw those groups in on the product. Okay? What would you predict then for the preference for forming the bromine with the R configuration or the bromine with the S configuration? Could you predict which one you would expect to be the major product and which one the minor product?
S will be the major.
The S will be the major product, right? Because if this top is more crowded, this one is going to be slower, and this bottom addition is going to be faster. Now we have a way to change the difference in rates of the reaction from one side or the other in the production of the new stereocenter. This is something we refer to as a stereoselective reaction. We generated a stereocenter, and we have some selectivity because now we've changed the steric environment from one side versus the other by having something else making it now asymmetric. Okay, it's no longer a symmetric intermediate. Each side is no longer symmetric. So the two reaction pathways will have different energies. So it'll be a slightly higher energy pathway to go this if it's more crowded than this. So you'll get less of that and more of this. That's the general concept, and that's true for any reaction where you now have chirality influencing the formation of a new chiral center. Okay? The amount of that influence, of course, is completely going to depend on the difference in energy and how crowded and how much you block one side versus the other. So then the level of selectivity could vary a lot. It could vary a lot. Okay, and we'll talk a little bit more about that. Now, let me just back up once and show you those products again. So now, if I look at those products of that hypothetical reaction that I had up there, right? Now we have a molecule with two stereocenters in it. We started with one, which was the R configuration. We start with one, which is the R configuration. We've produced a new stereocenter. We have a mixture now, which is no longer 50-50. It'll be something other than 50-50. But now we have a molecule where there are two stereocenters. What is the relationship between those two molecules? Are they mirror images? They're not mirror images. Okay? Look, if it was a mirror image, and there's each stereocenter would have the opposite configuration. So yes, the R configuration is S here. That particular carbon has the opposite configuration, but this R is the same. That's not a mirror image at that center. So these molecules can't be mirror images. Well, what are they? They're not the same molecule. They're not mirror images. They're not constitutional isomers, but they are different in their three-dimensional arrangements of all the groups, right? They are stereoisomers, but now there's another kind. Isomers, which are only different in their three-dimensional orientations, or they're stereoisomers, but are not mirror images of each other. That is what we call a diastereomer. And that's this, diastereomer. Okay? Stereoisomers that are not mirror images. That's the simplest definition. Enantiomers are stereoisomers which are mirror images. These are everything else. Okay? So stereoisomers, now we have two kinds. We have enantiomers, mirror images, and we have diastereomers, not mirror images. They're isomers of each other. They have all the same atoms bonded to the same atoms. They're just arranged differently in space, but they're not mirror images of each other. Okay? And we've seen examples of diastereomers that are not mirror images, even before this week. That happens to be cis and trans, using E and Z. These are not even chiral molecules, but they fit this definition. When we have isomers which are trans and cis, or E and Z, or cis and trans on a ring, they're not chiral molecules. If you took the mirror image of this flat molecule, it'd still be the same flat molecule. If you took the mirror image of this flat molecule, it'd still be the same flat molecule. Those cyclohexanes, they have that particular substitution has a plane of symmetry. So if you bisect the molecule here with a plane going right through the board, there's a plane of symmetry there. There's a plane of symmetry here. But these are no longer identical, right? But the mirror image of this would still be the same, and the mirror image of this would still be the same. Okay? So these are stereoisomers, which are not mirror images. These are also a form of diastereomers. Okay? That's a little different than the diastereomer I just showed on the previous slide with those two stereocenters in it. Those are what we refer to as configurational diastereomers. These are cis-trans diastereomers. Okay, those could be chiral. These are not chiral. I know it's a lot, right? A lot of different concepts. Let's just take a look at another example of configurational diastereomers. And I go back to this molecule. Anybody remember what this molecule is? Huh? Not malic acid. It's tartaric acid. Tartaric acid, famous Louis Pasteur, separated the tartrate salts from wine crystals, right? I've written it in a little bit different configuration, so I could have written this, like this. I've just written this in a different conformation. Notice instead of being in the completely open chain, I've drawn it with the carbons in this orientation rather than this orientation for the 4 carbons. So this is the same molecule as this one. At least I hope I have the same stereoisomer. I just rotated this bond to get this. Okay, I rotated that bond. So get used to seeing that too. We can orient molecules in different ways and even show a different rotational conformation. Keep in mind, this and this are equal. I've just drawn it in a different way. Okay, but let's take a look at this. This is a tartaric acid, has 2 stereocenters, one here and one here. Okay, what's the configuration? There's the mirror image of that molecule. Okay, and if I look at the specific configurations for each of those stereocenters, I see this is the S configuration, and this is the S configuration. And the mirror image would have R and R. It's easy to see the relationship if you look at the configurations, right? S's become R's. Every S or every position that has a stereocenter is reversed completely. Okay, those have to be enantiomers, right? Now, what if I start with a molecule instead of SS, which becomes RR, now has an SR? Okay? The relationship between this molecule and the one on the left, they're not mirror images of each other. S and S are the same, S are different. That's a diastereomer. The same thing, the relationship between this molecule and the one on the right. They're not the same, it's a different diastereomer. So that's how the relationship between these molecules exists. Those are mirror images of each other, enantiomers, but if you compare these two, those are diastereomers, and if you compare those two, those are diastereomers. Okay? On Friday, we're going to talk a little bit more detail about this particular molecule on the bottom and take a close look at its mirror image. All right? I'll see you Friday.